So that's a work that I did with one of my students, and we're gonna go through some electric field measurements and how to classify them using AI. So first, let's go to a brief introduction here. So lightning can be divided mainly in two main types, like the one that remains in the cloud, the intra-cloud lightning flashes, and the cloud to ground, the ones that touch the ground. And they have like different features in their electric field signals. So for example, the cloud to ground, they have like short rise times and slow decay times, depends on the distance you measure those electric fields. And intra-cloud flashes, usually they have like narrow pulses, they are bipolar, and they have sometimes crazy wave shapes. Okay, when we measure them in VLF, the very low frequency, they have this kind of swing wave shape, and they are more or less similar from each other. Though the characteristics that I just mentioned, they are when we measure in wideband. However, the lightning counters, they measure lightning electric fields in VLF. Okay, and then they count the amount of lightning that happens around the sensor. But nowadays we have a bunch of lightning location systems deployed everywhere. And why we should care about lightning counters? Well, lightning location systems are not everywhere. So they are almost everywhere around the world, but still there are some places that we don't have sensors. For example, in the middle of the Amazon region, it's super hard to deploy sensors, and it's super hard to maintain the sensors over there. We don't have internet connection. So for those very remote regions, probably single stations are the best solutions. Okay, lightning classification. So the traditional lightning classification methods face some limitations. So using AI, probably it's a good direction to improve the performance of the lightning location systems and also the classification of like electric fields in general. So over the past, I would say 5 or 6 years, a lot of people have tried to apply AI to classify lightning electric fields using different machine learning modules. We can use support vector machines, multi-layer perceptron, convolutional neural networks, residual neural networks. All those models we can apply to lightning electric field signals and try to classify them. But there are like some difference between them. If you have infinite computer power, you can use either one. But if you have a limitation in computer power, probably you need to pick the one that's like less heavy to apply your module. So in this study, I'm going to present a new methodology to classify between IC and CG using VLF. All the previous works, they use wideband electric field signals, and now is the first time that we apply AI to classify VLF. Okay, the data set here, we use a data set that comes from 3 different stations, one in the US and 2 in Brazil. So the system recording VLF from 7 kilohertz to 15 kilohertz. The data set is composed by more than 4,000 waveforms. And here are some examples of electric field signatures recorded either in wideband and in VLF. As you can see here, let's see if I can. Nice. So the blue lines are the wideband signatures and the VLF are in the red. So our data set is composed by positive and negative cloud to ground. And we also decided to include the compact intercloud, either positive and negative, because they are very distinct IC flashes. and all the other regular intercloud flashes, they are in the last class over there. Okay. Well, one of the goals of this study is also reduce the number of samples so we can feed the machine learning model with less data. So we reduce the sample size from 1 megahertz to up to 62.5 kilohertz. So that is, we can do that because we are working with VLF signals in which the upper limit frequency is 15 kilohertz. So we can see that we don't change much the wave shape of the electric field signal. Okay, also another technique that we apply in this study is to balance the data set. So the data set, the usually single station lightning data set is not balanced because of the characteristics, like the physics of the lightning flashes. So most of the time, most of the lightning, they are negative CG, and we have very, very few positive CG. So we need to balance the data set. And we use the smolt technique to balance our data set. So we can train the model with the same amount of data in all classes. Okay, we made different models here. One was using all the 5 classes, but we also try to do binary classification. So we made one model that has all the classes, and then we made binary models that has the classification only between CG and IC, and then once they classify between CG and IC, I also can do the classification between CG and compact intercloud, because usually the lightning location system, they misclassify between them. So, and also include the 2 different polarities. Okay, let's move to the results now. Well, so that's the results for the module with the 5 classes. So as we can see in the diagonal here, that all the classes are beyond like 90%, which is good for us. So even that the positive CG that most of the time is misclassified, we got 90%. So this is a proof of concept that we are able to classify lightning electric field events in VLF. We have here the result for the binary classification model, so which is even better. So we have a recall of more than 97%, which is like very good for lightning classification. So if we deploy this in a lightning counter, we can guarantee that more than 97% of the events will be correctly classified. And that is the result for the classification between CG and compact intercloud, which is really good. But as we can see here, always we struggle in classifying positive flashes, mostly because we don't have much data for positive flashes, because they are rare, they do not happen very often. And finally, the biggest achievement of this project is the implementation at a microcontroller level. So it's the first time that we apply an AI for lightning classification at a microcontroller level. So we don't need like a big data center to process and to run our model. We were able to implement the model inside a tiny microcontroller, so we can apply the classification model in the very edge of the system. Another achievement is that the classification time is only 254 microseconds. So we can classify each electric field pulse at every 254 microseconds, which is like more than enough for an interstroke interval, for example. So, in summary, AI-based solutions in the lightning classification text present a significant achievement over traditional methods. Our classifier, using a data sample at about 62 kilosamples per second, has a good accuracy, more than 97%. The model showed a very high performance across all types of lightning flashes that we include in our data set. The simplified binary model, which is applicable for the lightning counters, we had a recall exceeding 97%, and the classification time is less than 300 microseconds for a microcontroller that we applied here. So thank you, and if you need like more details, you can visit that paper. Thank you.
Thank you very much for your presentation. So